we have kind of a built theory of integration, how to integrate with respect to the Brownian motion in particular. So not what we like to do, we would like to take some benefits out of this theory actually. Okay? So we're going to start doing really the calculus based on this theory of integration actually. Okay? So that's what the let's start with the question. In Newtonian version of calculus, we know that if you have something like this, that if you want to integrate, for example, say a function that looks like this, f prime of g of s and g prime of s, say ds, okay, and then f and g satisfies good assumptions, then what would be the outcome of it? So the outcome of this is going to be, f of, by the fundamental theorem of calculus, f of g of t minus f of g of a. Okay? The same would be true even if I rather take an abstract instant t here. So this would be true. Okay? So we have the fundamental theorem of calculus. Question: are we going to have a similar kind of an identity? In other words, if I have the question of this, is this identity true? That if I have to integrate, say, from a to t, a function of a Brownian motion with respect to a Brownian motion, are we going to get something like this? Okay. So in other words, does this rule holds here? And the answer is no. Why? You can take, say, for example, integrate simply Brownian motion with respect to the Brownian motion. Okay. Then what is this integral? If someone remembers, so it's going to be w squared t over 2 minus t actually. Okay? Maybe s minus s, and you need to integrate it over 8t. So this is what what the example that we did when we were kind of when we defined and gave the different examples of this classic integral. Now what does this mean? This means that you have w square of t by 2 minus w square of a by 2 and yes, minus t minus 2, something like that. So you have this additional term coming out of integrating with w of t. Okay? So this rule is not true in general. Okay? Because if this would be true, we shouldn't have this term. Okay? The question is, if this is not true, then which statement is a true statement? Okay? So let's reflect and ponder over it actually. So imagine you have this interval a to t. Okay? Let me some arbitrary instant. And let's break down this interval into a mesh actually. Okay? Where I say that t naught is a and this is t1 and t2 and maybe the nth instant is t actually. Okay? And I want to compute, for example, this difference, which is f of motion minus f of w of a. Okay, so that's what I would like to compute, and I would like to see this is equal to what in the sense of the integral actually. Then what can be done is that I can write this as a telescopic sum that goes from say 1 to n, and that looks like this actually, f of w of ti minus f of w of ti minus 1 actually. Okay? So you can write it in this manner. Alright? And then if I assume, so you need to, so you know, that rule holds under certain assumptions actually. Okay? The continuity of f and you know, if you are in the assumption, so Leibnizian rule holds if you are under the assumptions of fundamental theorem of calculus actually. So if I want to get a similar kind of an expression, that okay, like this difference will be equal to what in the integral terms, then we need to have some assumptions actually, and let's assume, you know, that assumption is that, let's assume that f is of you know, C2 class actually. Okay, let's assume that f is of C2 class is 2 times differentiable actually. You can differentiate it 2 times. Okay, and let's see if we assume that f is differentiable 2 times, twice differentiable, then what result we get. So what I'm going to do on this increment of the Brownian motion, I'm going to apply, you know, what is called the Taylor expansion actually. Okay, so someone remembers the statement of Taylor expansion? So here's a statement of Taylor expansion. For example, if you have you know, you started with say x naught, so you want to, for example, do the Taylor expansion around a point x naught actually, and you want to truncate it onto, you know, first order term. In other words, the remainder is of the second order. Then how does this is going to look like? So it's going to be f of x minus f of x naught, okay, and it's going to be say f prime of x naught times x minus x naught, okay, plus f double prime. So if you want to truncate your expansion, for example, on, you know, up to the first order term, then you need to write the remainder term actually. And how does the remainder term is going to look like? The remainder term would be that there exists a point, for example, z, okay, you know, between what? Between x naught and x, such that is f double prime of z. Let me write it more explicitly, that how does this z is going to be in the terms of x and x naught. So I can, you know, write this as what? So say it's going to be some x naught plus lambda times x minus x naught. Okay, so that is really an arbitrary, you know, number, small number between 0 and 1, if you assume that lambda is between 0 and 1 actually. Okay, so it's a number between 0 and 1. So some number between 0 and 1 times x minus x naught square by 2 factors. Okay, so it's going to be the remainder. And now here I am saying that on the place of x, here replace w of pi, and on the place of x naught replace w of pi minus 1. Okay? So then what you're going to get, how does this sum is going to look like? So this sum is going to look like this actually, f of wt minus f of Brownian motion evaluated at a is going to be equal to the sum of substituting values here. In fact, I can, since you have 2 terms, so I can write, so you're going to have 2 sums actually. So the first sum is going to be sum, say f prime of, explicitly, w pi minus 1 times w pi minus 1 minus w of wti minus w of ti minus 1. Right? So that would be first term plus 1/2 sum I equal to 1 to n. Okay? And f double prime of, say, w of ti minus 1 plus lambda times w of, okay, w of ti minus w of ti minus 1, okay, times times what? times W of Ti WTi minus WTi minus 1 square actually. Okay. So you value, alright, that's fine. You value one convention actually. So I'm just putting everything in once the subscript. So we're going to have something like this. Are we happy with it? Okay. Now, here's a rough argument. What will happen if I'll increase n? In other words, I'll make, for example, more bigger and bigger mesh actually. Okay. What will happen that if I take this limit in L2 omega sense actually? Okay. What will happen that if I take this limit in L2 omega sense? Then this guy is going to be, any guesses?
Left limit.
So it's going to be left limit. It's going to be equal to a to b, a to t, okay, and f of w of t, dw of t. You agree?
F prime or F?
F prime, yes. Okay. It's going to be something like that. I'll justify it more rigorously. Okay, so at the moment you may assume that I'm giving a heuristic argument actually. And how about this term? So this second term, okay, could be a to, so you have 1/2 and a to t, okay, and a to t what? A to t. So I know that the Brownian motion has quadratic variations actually. Okay, so this will, under the expectations, okay, will turn out to be ti minus 1 actually. So roughly, heuristically, I'm going to justify it. Okay, so at the moment you may assume it, I'm going to justify it later when I'm going to write the proof of so-called lemma. I'm going to get into the details of it. But this is roughly going to be f double prime of w of t and ds have to be, if I'm writing t here, I should write s everywhere. So I'm going to have something like this. Okay? I'm going to have something like this. Is it making sense? Okay. So this is the term really, that makes Leibnizian calculus, the Newtonian calculus different from the Ito calculus actually. This is the term. Otherwise, if you look at the Leibnizian calculus or the Newtonian calculus, fundamental theorem of calculus is really, in that you don't have such a term. So this is really the correction term, whatever you call it. It's a term that appears. And I'm going to prove that this is going to be true in L2 omega, but I know that if this identity is true in L2 omega, this is also going to be true in probability. Okay, so the convergence in L2 omega implies the convergence in probability, and you can also have this convergence almost surely, but not for what do you call this sequence, but a subsequence actually. So I'm going to get a version of almost sure convergence. So let me summarize what I have done. Okay. So I'll do the proof, a detailed proof of it, but not now. I would like to talk in general about the things first and what are the advantages of doing it. Okay. So the result that I am writing is, so here's the theorem. Okay, so this theorem is called, really the simplest form of lemma. It's the simplest form of lemma. So what does it say? It says if I have a function that is C2 class, okay, and it depends only on x actually. It depends on x, it doesn't depend on, it's just a single variable function x. Then f of w.r.t minus f of w.a, okay, is going to be equal to what? A to t f prime of w of s t w of s plus 1/2 a to t f w prime of w of s and ds. Okay? So this is what you're going to get. And this is true almost surely. Okay? Should be true almost surely. Because if you have, this convergence in L to omega, you can have convergence in probability, and that implies the existence of a subsequence for which the same identity would be true almost surely. Okay? Now, as I said, this term makes really different, this term makes really Newtonian calculus different from, Ito calculus actually. Can you see it actually? Think about it. If W would be an arbitrary or simple function, then you're going to have something like this as a result coming from Ito calculus. Okay? Alright. Now, for the sake of convenience, rather than writing this statement or such kind of a statement again and again and again, I'm going to introduce a cryptic form of writing this, what do you call, result, okay, or this formula. And the cryptic form of writing this result is this. So I'm going to say, if I have a function of Brownian motion, and I'm interested in computing the differential of it. So I have a function of Brownian motion, and I have, I'm interested in computing the differential of it. Then the differential of it is equal to f prime of w of t dt plus dwt plus 1/2 f double prime of w of t dt. So this is going to be my dynamics actually. Okay. You getting the point? So this and this are the same things. So when I'm going to write this, I'm going to mean this actually. Okay? But there is a convenient notation you're going to see later on that this is a very convenient notation if you want to write it in a differential format. Okay? Now what is the benefit of having this kind of a formula? Imagine you have a particle, okay? Or imagine you have something whose motion is random, okay? Whose motion follows whose displacement is random actually, okay? Moving in a random fashion. So it follows a Brownian path actually, okay? And then you have something that depends on the displacement. So what are the things physically that depends on displacement actually? Can you velocity, acceleration, speed, forces, and all these things are really the function of displacement. You can treat them as a function of displacement. And now you're going to say that, okay, I know that that's how the particle is displacing. What would be the dynamics of the force that depends on this displacement actually? Okay? So if I know the dynamics of the particle, then what would be the dynamics of the force that depends on that particle? What would be the dynamics of the velocity that depends on the particle actually? Okay? Because all these functions, all these quantities are going to be the quantities depending on this fundamental quantity, displacement actually. The question is, okay, if I have a quantity that depends on this random displacement of the particle, how that quantity itself would change actually over the time, how that quantity would evolve over the time. The answer is this would be the dynamics of it. This would be the dynamics of it. We're going to do lots of examples of it.
So dynamic means someone
Dynamics, similar differential. So I'm going to say differential. Okay. So in other words, you are saying that okay, I have this some f that depends on w of t, which is kind of representing displacement of the particle, and I want to know how this f is changing over the time, how this f is evolving over the time actually. Okay, how this displacement is evolving over the time. Okay, I know that kinetic energy of a particle depends on velocity. Okay, and if velocity depends on displacement, which is Brownian motion, I want to know how the kinetic energy of the particle would change over the time actually. Because the kinetic energy is a function of displacement actually, a function of velocity. Are you getting the point? So this differential tells you, okay, that now you can talk about the dynamics of the quantities which depends on the random quantity actually. So you're learning an interesting kind of calculus actually. Okay? And as I said, this is a cryptic way of writing this identity. It's a cryptic way. It's a shortcut. So whenever I'm going to write this, I'm going to mean this. Okay? Now, what are the advantages of the formula? Think about it. What are the advantages of the formula? There are lots and lots of advantages of the formula. Think about it. So now, if I want to compute, for example, the differential of the square of the Brownian motion actually. Okay. So what would be the differential of the square of the Brownian motion? Okay. You just have to think that, okay, that means that my function here is x square. So the differential of the square of the Brownian motion is really what? F prime of t, which is going to be 2 w of t dwt, okay, plus, okay, 1/2 of
times 2.
4 is going to be so only 2, so 2 will go away and you're going to get simply w of t new. So it's going to be simply dt. It's going to be simply dt. Are you getting the point? And what is the actual meaning of this expression actually? The actual meaning of this expression is that if you integrate from a to t this w square of s, okay, with respect to, for example, ds, okay, then the better is, you are saying that w square of t minus w square of a is equal to integral from a to t of f prime of w of t, which is going to be f prime. F prime is 2x actually. You just need to substitute values here. Okay. You have to do the 2 w of s dw of s, okay, and plus 1/2, which is going to be 2 only, okay, and 2 only, and f double prime is going to be only ds, okay, from a to t. This is going to be, okay, it's going to be dt or what? Dto. So that's what it's going to be. Perfect. Are you getting the point? Am I writing the last term correctly? A to t, fw prime is, okay, that's what.
So that would become t minus a.
Now, what is another advantage of it? This formula. Now think about it. Imagine you are set to compute the, really the integral of this function actually, w of s. Now you're going to say the integral is this minus this actually. Okay? Think about it. So this formula also says that okay, if you want to find the integral of, for example, some function with respect to the Brownian motion, you have to just figure it out, okay, what is the function whose derivative that integrand is actually. Okay? Because once you know that, then you can just substitute values here and you have the integral. For example, if I say you compute this integral for me, from a to t sine of say w of t and dw of t. So what are you going to do? How this formula is going to help you out?
Minus cos.
So you have to just think that, okay, if I take, what you're going to take? If I take f to be
Sin x.
minus cos x and I substitute values there, I have an integral of what you call this is stochastic integral in terms of this increment and a Riemann integral. Okay, a Riemann integral.
I said, how would Riemann integral be solved?
Okay, so you can't solve it. So you have only you can only numerically do it if you have to deal with it actually. You can't explicitly solve it obviously. In some cases it would be possible to solve it, not in the many cases actually. But at least you knew how to compute the stochastic integral of it. Okay? Is it making sense? Or so what are the advantages of it? That's an immediate advantage of it. So one advantage is that it allows you to compute the function of differential of function of Brownian motion. Okay? In other words, it allows you to compute that how to integrate some function of Brownian motion with respect to Brownian motion. Okay? So that's what is really one of the key things. So now what we're going to do, we're going to extend this analysis. So my function currently is like this. So it's like a function of x actually. Okay, where x is, we need x by Brownian motion actually. But now, so it's a kind of an autonomous function which doesn't depend on the time actually. Okay. Explicitly. Obviously Brownian motion depends on time, but it doesn't depend on time. So next thing would be that what if I have a function that depends on time and Brownian motion, what would be the dynamics of such kind of a such kind of a function? Okay. So let's do what would be the dynamics of such kind of a function. Okay. So what do you think, how we're going to do? We're going to do what we did here, precisely the same. Okay, we're going to start with a Taylor expansion, take limits and try to come up with a kind of a integral version of an E2 formula. So that's an E2 formula, simplest form of E2 formula, when function is only a function of Brownian motion. Okay. So let's extend this analysis to the next level. I'm going to prove one version of it, maybe the simplest version or this version, and the rest are similar actually. Okay, so I'm not going to get into the all proof. If you wish, you can read it from Kapensky or from here actually. Okay, so let's slightly generalize this formula. Okay, so we're going to do a slight generalization of it. So instead of now f, imagine I have a function that depends on t and x, and by x I mean Brownian motion. So what we're going to do? So from where we're going to start? We're going to start with this assumption. So suppose that now f is still C2 class actually. But what would be the meaning of C2 class now? So now the meaning of C2 class is going to be that its first order derivative with respect to time and x, and it's all kind of second order derivative with respect to time and x. Okay? With respect to time and x are continuous. Take it?
सही है.
That's what I mean. So that is going to be my assumption. And now I'm going to do what? I'm going to do the same. So let's say I would like to evaluate this increment, the f of w of t minus f of w of f of a and